This is MEI Statistics Minor, Discrete Random Variables for the Geometric Distribution. Our first video, 4.1, Introduction to the Geometric Distribution. For a binomial distribution, we recall our assumptions as follows. There are two possible outcomes of each trial, success or failure. The probability P of success at each trial is constant. Trials are independent of one another. The number of trials n is fixed. Now, for a geometric distribution, there are still two possible outcomes of each trial, success or failure. The probability P of success at each trial is still constant. The trials are independent of one another. However, the number of trials n is no longer fixed. The random variable y, distributed geometrically with probability of success p, is the number of independent Bernoulli trials necessary for the first success. Not the number of successes, the number for the first success. Note that this number of trials also includes the first success. There is an alternative definition that it is the number of failures which are counted, but this is not in the spec, so the number of trials will include that first success. Now, for a binomial distribution, we know that the value of n is known and fixed and finite. But for the geometric distribution, there isn't a fixed number of independent trials. If you think about it, you could just keep on failing and failing and failing. It could be 27,000 before you get your first success. It could be even higher. So the binomial has a finite number of possible outcomes, and the geometric has an infinite number of possible outcomes, as does the Poisson. The Poisson goes up towards infinity as well. The kind of problem we might associate with the geometric distribution is as follows. Prime the probability that the third child born into a family is the first female. So if we're going to do it the old school way, we would consider a tree diagram. So we would need to consider first child, second child, and third child. And in each case, child is either female or not female. Now the probability of success, probability that a child is female, will be some value p, which we would put here and would run all the way through. The chance of not being a female is q, which we remember is 1 minus p. Now we want the probability that the third child is the first female. This means that the first child cannot be female. This means that the second child cannot be female. And it means that the third child must be female. So the probability of that is q times p, which is p times 1 minus p squared. Note that if we were looking whether the second child was the first female, we would have a single q and a single p. So we would lose that squared and that would become a power of 1. If we had a fourth child, we would need 3 non-female children and a fourth female, so that would become a cubed. So it's really only the power of q that is altering according to the value of x. So a discrete random variable with probability function, probability that x equals p times 1 minus p to the x minus 1 for x equals 1, 2, 3, where p is the probability of its success, follows a geometric distribution with parameter p, where that p must lie between 0 and 1. More formally, we would say probability that x is p times 1 minus p to the x minus 1, for x is a member of the natural numbers, otherwise known as the positive integers, or 0 otherwise. So if we look in GeoGebra at the shape of the distributions, we have on the top a binomial distribution with n currently set at 75 and p at 0.1, and a geometric down the bottom that of course isn't dependent on n, so that is just relying on the value of p. Now if I shift the value of p along, you notice that the binomial shifts along with the value of p. Its mean and mode and everything else with it shifts along, whereas the geometric stays quite near the origin. In fact, it's ever more skewed the higher my value of p. Here it's extremely skewed, whereas binomial with this high value of n is almost symmetrical all the way through. So if we're going to answer this question using the geometric distribution, first of all we need to think about the assumptions. So we need two possible outcomes of each trial, success or failure. Absolutely, we've got either female or not female. Probability P of success at each trial is constant. Yes, it's not quite 0.5, in fact it's roughly 0.49 to 2 decimal places. And it is debatable whether that is constant with each person, but it's a fair assumption for now, it's certainly close. Are they independent? Again, not quite, but they're close. It is a fine assumption for a model. If we're wondering if a situation should be modelled by a binomial or a geometric distribution, we need to look at a couple of things. The first is the assumption that differs between them, the fixed number of trials. The fixed number of trials is required for a binomial distribution, but not for a geometric. So when I see in a family of 5 children, I think to myself, that is a fixed number of children, I think that's binomial. Whereas up in A, there's nothing indicating that anything is fixed. The other thing that I need to look at is words like before the first, because that's what the geometric does. It counts up until the first success, whereas the binomial counts the number of successes, or indeed the number of failures. So A would be geometric, and B would certainly be binomial. Some further examples. How many times a coin must be flipped until a tail occurs? How many people must a representative from Everton Football Club Marketing Division randomly select from a street in Liverpool until he finds a person who attended the last home game? How many of her friends must a student ask, in turn, to guess the day of the week on which her mother was born before the day is correctly guessed? Now, if you're doing those in real life, you'd need to very carefully consider the assumptions, but these are the kinds of questions that would be modelled by geometric distribution. So the next video, we are going to be calculating probabilities for the geometric distribution.